I'm going to talk about a protocol for fast privacy-preserving distance computation and biometric identification. And I'm actually going to talk about two works. The GSHADE paper is joint work with a student of mine, Michael Sohner, and researchers from Morpho, which is a company building biometric systems. And another paper which I use as a baseline for this work is joint work with Michael Sohner and Gilad Asharov and Yehuda Lindel from Bailan. The protocol we will build can be used for the following setting, namely for biometric identification. On the one hand, we have one biometric, and a face, for example, X, and on the other side, we have a database of biometrics, a database of faces, and we want to check whether this face here is similar to one of these faces in the database, but we don't want to send the image to the database as it's done in today's systems, for example, in border control applications or so. And we also don't want to reveal the database to the camera, right? And the challenge here is, because we're dealing with biometrics, we want to check similarity. So not direct matches, not identical matches, but only similar features. And we want to preserve privacy as much as we can. So stepping back one step, this is just an instance of a very general problem, which is called secure two-party computation, where we have two parties, Alice and Bob. They provide their inputs, X and Y, and they want to compute a joint function on these inputs. And in the end, both learn the output of this function. And this is a long-studied problem, studied since the 80s, and many optimizations have been proposed. And in this talk, I'm going to focus on passive adversaries only. So we assume everybody in the setting is following the protocol. Nobody's going to cheat. And having security against stronger adversaries is mainly future work for what we do. So this secure two-party computation has plenty of applications going back all the way back to work by Nauer and Pinkers for auctions, remote diagnostics to check where a program failed without revealing the memory trace of your operating system, DNA searching, biometric identification for many biometrics, fingerprints, irises, faces, hand shapes, and so on, going all the way to medical diagnostics, whatever you can imagine. Essentially, everything is doable. So one very main ingredient of these protocols is a sub-protocol which is called Oblivious Transfer, and we will build heavily on this, and I spent quite some time on explaining you how to efficiently build OT, and then later on we will see how to build the entire biometric recognition from OT. So Oblivious Transfer is a very simple protocol where Alice provides two messages, X0 and X1, and Bob provides one bit, and he says, I want to get either the message X0 or the message X1. And this basic primitive can be used essentially to build everything on top of that. So where is OT used? One very classical example is Yao's garbled circuit protocol going back all the way to '86. And this is a protocol for secure two-party computation. With that protocol, you can compute any functionality. And as an example, I take the comparison functionality to compare two inputs. So how does it work? The parties have their inputs, X and Y. And now they construct a Boolean circuit that computes the function. Comparison circuit, for example, looks like this, consisting of these gates here, and the bits go in there, and then there are some carries, and in the end, they get the output. So now the construction of Yao, instead of computing on bits, Yao proposed to use two keys for each intermediate value there. Instead of computing on bits, you compute now on keys. And instead of applying a Boolean operation, you encrypt the output keys with the input keys. And then later on, for each gate, such encryption tables are built and sent over to the other party. And this party sends the keys corresponding to its input, Y, over to the other party. And then they run this Oblivious Transfer protocol such that Alice gets the keys that correspond to her inputs, but no other information. And then she can use these encryption tables to decrypt the output of the functionality. And here we see in this widely used, or this very efficient protocol, it's not used yet so much, we need one OT for each input of Alice. Another example is the GMW protocol, which also allows to compute an arbitrary Boolean circuit on the private inputs. It works as follows. Instead of computing on keys, now the parties compute on shares. So they take their inputs, A and B in this example, they secret share them among them, and then they can locally compute an XOR gate. They just take their own shares and XOR them, and then they get the shares of the intermediate value here. That's easy for XOR gates, but for AND gates, they need a new interactive protocol to evaluate AND gates, where they input their own shares, and in the end, they get the output shares of this intermediate wire. And in the end, they recombine their shares to get the output of the computation. And these AND gates require 2 oblivious transfers per each AND gate. So that's the outline of the talk now. Speaking about efficiency, it's widely accepted that public key crypto is much slower than symmetric crypto, is much slower than one-time pad operations. So what I've shown you already are that we have generic protocols for computing arbitrary Boolean circuits, either YAO or GMW. They heavily use OT inside. And then YAO uses some symmetric crypto operations to encrypt and decrypt these tables. And the GMW protocol essentially does one-time bit operations, XORs of bit strings. So that's what I showed you already. And in the first part of the talk, I'll show you how to very efficiently build Oblivious Transfer using a few public key operations and many symmetric crypto operations. And then in the second part of the talk, I will show you how to build this actual biometric, privacy-preserving biometric recognition protocol from OT, and only from OT. OK, so the first part, how can we build highly efficient OT extensions? And this is, as I said, joint work with Gilad Asherov, Yuri Lindell, and Michael Zoner, where we optimized Oblivious Transfer extensions. So first of all, OT, there are bad news about OT. Namely, there's no black box reduction from Oblivious Transfer to one-way functions. So we need public key crypto somewhere in the protocol, and we try to reduce it as low as possible. There are several OT protocols that are indeed based on public key crypto. The most efficient, to our knowledge, is the one by Nauer and Pinkers. And if you implement it on today's hardware or on standard PCs, you get about 1,000 OTs per second. Hence, public key crypto was widely believed to, Oblivious Transfer was widely believed to be relatively expensive because public key crypto is expensive. So people try to avoid OT in building efficient protocols because they thought we can only do 1,000 OTs per second, which was a problem. So there's good news about OT. Beaver in '95 showed that you can pre-compute these OTs, and later on, when you need them in the actual protocol run, you can essentially do one-time pad encryption. So you can shift all the workload into an early phase of your protocol. And then there's works about Oblivious Transfer extensions, which is in conceptually very similar to hybrid encryption. So if you want to encrypt a long message using public key crypto, what do? You take a symmetric encryption, encrypt the message with a fast symmetric crypto, and then take this short key and encrypt it with the expensive public key crypto. And the same can be done with Oblivious Transfers, which is called Oblivious Transfer extensions. So Beaver showed how to do Oblivious Transfer on really long strings using only small, short OTs, and then stretch them into long OTs. And that's the way you would expect it. You take a pseudonym function and generate a long mask, and then use this as a one-time pad. And then there's work started by Ishai et al. on Oblivious Transfer extensions how you get many of these OTs using only a few of these real base OTs. So in our work, what we did is we optimized this Oblivious Transfer extension protocol of GSHADE. And this protocol looks as follows, the original protocol by GSHADE. We want to do many of these 1 out of 2 OTs. And M is here, think about it in the order of billions or millions or billions of OTs you want to do. Alice inputs pairs of bit strings. Bob's inputs inputs his choices and gets back the chosen messages. And the protocol works in 4 phases, which I will show you in the following. So in the first phase, Alice and Bob run a few seed OTs called base OTs here. And this K is a security parameter. Think about 80 or so base OTs you need to run. And they run these OTs in the opposite direction. So Bob here chooses random masks as inputs. Alice chooses random bits as inputs, and they run the base OTs, 80 of them. So in the next phase, Bob generates a random matrix T and uses the seeds from the base OTs stretched by a pseudo-random generator and exhausts this with a mask, with this matrix T, and with his choice from the actual OTs they want to run. Then he sends over these 2 values for each OT, and Alice does a similar thing. She takes the seeds obtained from the base OTs, puts them into a pseudo-random generator, and unmasks one of the values obtained here. And the PRG can be instantiated, for example, with AES, which is highly efficient on today's CPUs. The next step is both parties take these matrices and just transpose them. They flip them from a row-wise representation to a column-wise representation, which looks very simple. And then they use the actual messages and mask them with a hash function applied to this matrix V here. And then Alice sends over 2 values, and Bob can decrypt later on. That's the protocol. So this is the protocol as a whole, which I already showed you. So if you look at the computation complexity, it looks pretty good. So Alice does 1 PRG evaluation here, and 2 hash function evaluation. Bob does 2 PRG evaluations and 1 hash function evaluation. And now we took this protocol and implemented it in a straightforward way. And we did some micro benchmarks where the time is spent in the protocol. So for 10 million OTs, which took 21 seconds, we saw that 1% of the runtime was spent on the base OTs, which is as expected. It's 80 base OTs, and we don't need much there. The hash function is pretty expensive. We used SHA-1 there, and it was 33% of the runtime. Also, as expected, the PRG is much more efficient because we can use AES, and it was 14%. What was crazy to see is 42% of the time was spent in transposing a 10 million by 80 bit matrix, just matrix transposition. And the problem was we just did it the obvious way. We took the bit here and put it there. We took the bit here, put it there. So we have 10 million times 80 operations spent only for matrix transposition, and that was 42%, almost half of the runtime was spent by a simple operation, which nobody designing the protocol would consider as being the crucial thing. And there was a bit of network overhead and XOR operations that just was 10%. So the message here, if you want to design efficient protocols, you should not only count the number of crypto operations, you should also look at the seemingly trivial parts, which in the end were critical here. So that's what I already said. We had these 10 million times 80 lot store operations there. Instead, what we now use is there are more efficient matrix transposition algorithms. One is due to Eglund, and it takes only m times log k swap operations. And it works as follows. It first swaps the elements on the diagonals here, and then swaps blocks of them, and you have log k of these iteration steps, and each has about O of m operations. So this is much more efficient. And overall, it made transposing the matrix 10 times faster using this algorithm instead of using a trivial one. So the next observation is this protocol is very nice to parallelize because this matrix, we can just split the matrix into chunks and assign a separate processor thread to each of these chunks. So that's also very convenient because on today's CPUs we have 4 or 8 or even more cores, so we can use parallelism to get better runtimes. So let's look at the communication complexity. So Alice sends 2 L bits in this message here, and Bob sends 2K bits in this message. Now it depends on the application how big the payload data is. For example, for Yao, we send keys, so we have the communication is the same in both directions. For GMW, the payload is only 1 bit of information which is sent in this message here. So most of the communication now is this message from Bob to Alice. So what we observed now is we don't need to generate this matrix here randomly. Instead, we can massage the protocol a bit such that this matrix here is directly the output of the PRG, and then we only send this single value instead of sending 2 values. So overall, this simple trick reduces communication by a factor of 2. And now the other observation is we can do a similar thing for the messages. Sometimes we don't want to put the messages into the protocol. It is sometimes also sufficient if the protocol outputs the messages. So, for example, for Yao's protocol, it's okay if one of the messages is generated by the protocol and the other one is correlated to the first message. And we call this correlated OT, where the first message is random and the other one is correlated. And we also have for GMW, it's sufficient if we have random inputs into OT. So both messages are now randomly generated in the protocol, and this is called random oblivious transfer. So for these 2 flavors of OT, which are actually used in protocols, we can get even better protocols using a similar trick. We let the one message be the output of the hash function, and the other one is the correlated one. So this allows us to send only 1 message here instead of 2. It again cuts the data in the opposite direction by a factor of 2. And the same for random OT, even better. We take the 2 messages to be the outputs of the hash functions, and this completely eliminates the last message. So now these are the runtime results that we got. This is the original implementation measured. The green ones are over a gigabit LAN between 2 machines, and the others are over a standard Wi-Fi network between the protocols. And these are just the optimizations I showed you before. The first one was just this more efficient matrix transposition. It cut it down the computation for the fast network quite substantially. Then this general OT, where we cut down the communication in the one direction. It didn't do much because now the bottleneck was the message going in the other direction. As soon as we start to cut the other message, runtimes go down here by a factor of 2. Then this random OT is also a bit more efficient. And then using parallelism, 2 threads or 4 threads, we cut down the runtime over the fast network almost ideally. So we went from 20.6 seconds down to 2.6 seconds for the fast network, and for the slow network about a factor of 2 in actual runtimes. So the take-home message from this part is OT is highly efficient, and essentially what we see from these runtimes is that now the communication is the actual bottleneck for OT extension. So it's just a matter of sending 80 bits per OT in one direction, and all the crypto is using parallelism and everything. The network is the bottleneck, and computation is not essential for Oblivious Transfer. And these measurements were even without this AS new instruction set. So computation is even less critical using CPU support for crypto. So now we have highly efficient Oblivious Transfer. What can we do with it? And that's the second part, the GSHADE protocol. So this is, again, the motivation slide. We want to do privacy-preserving biometric identification, for example, for faces, as I showed you already. So what are use cases? Use cases are, for example, biometric access control, or a border control scenario in some countries when you want to enter, a picture is taken and this is matched against the database. This is also an application. Okay, another example is anonymous biometric credentials. So you could run the protocol between a database that, instead of giving back, yes, the face was in the database, gives back to you a credential, for example, a signature saying you're allowed to drink beer, and then you can take the signature and authorize against another party in an anonymous way. Another example would be a secure biometric database intersection. You could have two databases of faces, and they wanted to see who are common in the databases, and plenty others. Okay. Now, we don't do any fancy biometrics. We just take existing protocols and see how fast we can bring them. And one very nice example is the Cipher algorithm invented by Rita and Benny Pinkers and some others, presented at Oakland 2010. And they showed how to highly efficiently do all the biometrics. And in the end, the function that needs to be computed securely is you represent each face as a bit string of 900 bits. And what you need to do to compute securely is you compute the Hamming distance between 900 bit strings and compare this with a threshold. And depending on this comparison, if the Hamming distance is smaller than the threshold, then you find the match. So that's the functionality that needs to be computed, computing Hamming distances and doing a comparison with some thresholds. Okay. So this is a map of related works. In the rows, you see the different distances. For example, the Hamming distance I just showed you for face recognition. Then there are, you can use different metrics like Euclidean distances, for example, using eigenfaces. You get face recognition. There are approaches for fingerprint recognition, also using Euclidean distances, and normalized Hamming distances for iris recognition. And the first protocols that came out, they presented protocols based on public key crypto. So their main contribution was to show all the biometrics and all the feasibility it can be done at all. For faces here and eigenfaces there. Then subsequent works just took these protocols and tried to optimize performance of the underlying crypto protocols. So the first approaches tried, instead of using public key crypto for the entire protocol, they tried to do a hybrid of protocols where they, for arithmetic computations, they used public key crypto, and then later on for bit operations like comparisons or so, they used Yau's protocol or other protocols. So these are hybrid approaches, and there's a long list of them. And then the most recent ones are based on Oblivious Transfer directly. Instead of using public key crypto, they use these highly efficient Oblivious Transfers, and that's where our protocol comes in, which is called GSHADE. And it's based on a previous protocol called SHADE, which I'll show you in the following slide. So this is a paper by Bringer, Chabanet, and Patey, presented in 2013, and it shows how to compute the Hamming distance directly using OT. So the goal is to compute the Hamming distance between X and Y, and think of these as 900 bit strings for this face recognition algorithm. So we want to compute the sum of the XORs of the bits for these 900 bits. So the protocol works as follows. First, Alice chooses a random value Ri, and then adds to this value Ri its bits yi as the first message, and this is the second message. She inputs this into OT, Bob inputs his xi, and in the end, he obtains this message. And if you write the formulas down, you see that this r, which is the sum of these random choices, and this t, which is this r plus the Hamming distance. So in the end of the protocol, they have a secret shared value. Alice has r, and Bob has r plus the Hamming distance that they want to compute. And from that step on, it's easy to continue with generic MPC protocols like YAO or GMW, which I showed you before. You just subtract from this value t here this r using a small circuit, and then you directly have the Hamming distance, and you can continue as you like. So this is a very simple protocol, and the only ingredient is using OT in the protocol. Okay, so we did a couple of observations now on this GSHADE protocol. The first observation is, in our application, we want to compute multiple Hamming distances. We want to compare this one phase X with the first image, the first phase in the database, YY, Y1, with the second in the database, and so on. So we want to do many of them in parallel. Of course, we could run the protocol n times in parallel, but we can do better because instead of running the protocol on these short strings, we can just concatenate all these strings together and then run the same number of oblivious transfers just on longer messages. And this doesn't cost much in the OT extension protocol because it just, the expensive part is determined by the number of OTs. By concatenating the messages, we just run the same number of OTs, but on longer messages. And that doesn't cost anything, or not too much. OK, the second observation is we can use these correlated OTs, which are much more efficient than the random OTs. Why is that? Instead of choosing this R up front and then inputting the messages, the protocol can directly spit out this R, and then we have some correlated value as the second message. So we can use correlated OTs instead of real OTs there. And the third and main observation of our paper was we can actually generalize this protocol to a huge class of functions, namely all functions between x and y, that can be split up into the sum of a subfunction which depends only on x, a subfunction which depends only on y, and some sum of subfunctions that depend on the bits xi and this capital Y. And this is much more general, and I give you some examples below. So the Hamming distance is, we set these x and y as 0, and this other subfunction is the XOR of the bit strings, and this fits into this class. Another example are the squared Euclidean distance, which is used for faces and fingerprints. We have the f capital X is the sum of the xi squares, fy is the sum of the yi squares, and this intermediate term is this minus 2xi times yi. And this is exactly the squared Euclidean distance that's computed then. It also works, I don't give the concrete formulas, for normalized Hamming distances, which is used for iris recognition, where instead of computing only the Hamming distance, we have also masking bits that essentially determine which bits of the representation in the biometric are significant for the computation. And these masks are multiplied in here. And this can also be written in this form. And the squared Mahalanobis distance, which is used for handshake, keystroke, and signature recognition. It's also, if this matrix M in between is public, then this protocol can be used as well. OK, now we have this class of functions, and the protocol is essentially the same as before. But instead, we use here these intermediate terms, fi0y, fi1y as the two messages. And here we subtract the f capital Y, and here we add the capital X subfunctionality. And the protocol stays the same. It's just much more general than initially thought. And from that step on, we can continue as before with generic MPC to compute whatever, finding minimars, comparing with thresholds, whatever. This is highly efficient in circuits. OK, so that's this generalized GSHADE protocol. Okay, so these are now actual runtimes on a database with 5,000 entries, comparing one biometric against a database of 5,000. And these are the distances as showed before. And this are the real measured runtimes and communication, and it's all well below 10 seconds for faces, for fingerprints, finger codes, for iris codes. And the communication is quite reasonable. It's in the order less than 100 megabytes.
So what do you do? You are comparing a face with?
With 5,000 faces in the database. Yes. And the result, it depends. It gives whether a single bit if the match was found or not. And that's the entire protocol.
And how does this scale? I mean, that's a pretty small database.
It scales linearly essentially, in both parameters. It's essentially the number of OTs. It's the number of OTs stays the same, just the messages gets larger. So, so here are some comparisons with previous works, and here we only took the numbers from the papers. So the runtimes are somewhat debatable because it's not on the same machines, not using the same programming languages, and so on. So this is for sci-fi. The blue one is the public key-based protocol, then a protocol using garbled circuits in green, using GMW for the entire protocol in yellow, and this combination of GSHADE for the distance computation and GMW for doing the matching later. And on the left, you always see the runtimes, and on the right, you see the communication. I have to apologize. I couldn't convince my presentation tool to put these bars in the right direction. They are true. The log of 0.3 is negative, so these grow in the wrong direction. Okay, so we go down from, in runtime, this is runtime in seconds, from 244 seconds down to 0.2 seconds for 100 entries in the database, and this is for 50,000 entries. Our protocol takes 10 seconds for a database with 50,000 faces. Communication is also cut quite reasonable, from 7.3 megabytes down to 0.2 megabytes for 100 entries in the database. And that's for 50,000 database entries. We have 63 megabytes for the entire protocol. So similar for eigenfaces, also public key crypto, hybrid, GMW only, and this new approach. These are the runtimes. For 1,000 entries, we go from 100 something to 1.3 seconds. Communication is also in the same order, even a bit better than these hybrid protocols that used public key crypto. Usually why these hybrid protocols were used are because multiplications are very expensive to do in circuits. They have quadratic overhead. So these hybrid protocols usually do all the multiplications using public key crypto, essentially homomorphic encryption par year, and then do all the bit operations in garbled circuits. And they were previously the best in terms of communication. And we even get a bit better in terms of communication. OK, now iris codes. Similar here, computation is cut essentially. Communication goes a bit down because we have these normalized Hamming distances which add a bit more overhead to the protocols. And finally, finger codes. Also, computation is much better now, and communication is even a bit better than before. And all are in reasonable orders of magnitude. OK, to conclude, in the first part, I showed you that Oblivious Transfer is highly efficient due to OT extensions. In the second part, I showed you an application that can be built directly on Oblivious Transfer. And future works are further optimizing the communication of OT or secure computation in general. The computation is very low already. The communication is the actual bottleneck in today's implementations. Other applications that are based directly on Oblivious Transfer or using GSHADE for other distances We did some work together with Benny Pincus on having efficient set intersection protocols built directly on Oblivious Transfer or other applications. And finally, all I showed you is only for passive adversaries, and it's a great challenge to extend to more powerful adversaries. All right, that's the end. Thank you.